Hello and welcome to the AI Affairs podcast.
It's great to be here.
Today, we are initiating a deep dive into what might be the most, ambitious crossover event in the history of computing.
It really is a fascinating time to be looking at hardware.
Yeah, we're looking at a face-off, maybe even a shotgun marriage, between two revolutionary paradigms that are challenging everything we know about how computers think.
Well, for decades, we've been coasting on Moore's law,
Yeah.
right? Just making transistors smaller. But we are really reaching the physical limits of what we can do with traditional silicon.
The walls are closing in.
They are, the atomic wall, so everyone is scrambling for the next big escape route.
And it seems like we have two very different escape routes on the table. On one side of the ring, we've got the digital brain neuromorphic computing. It's trying to mimic biology. And on the other side, we have the reality simulator quantum computing, which tries to mimic the fundamental laws of physics.
That's a great way to frame it, biology versus physics.
But the real story we're unpacking today isn't just about them fighting for dominance. It's about how they're evolving, the massive hurdles they're overcoming, especially this concept of fault tolerance and the wild, almost sci-fi possibility that they might actually merge into a quantum brain.
That is the ultimate goal and, frankly, the holy grail of high-performance computing. You see, traditional computers are hitting a wall.
The von Neumann bottleneck.
Exactly. We need a way out. We're looking at two different maps. One map follows the extreme efficiency of the human brain, and the other follows the probabilistic power of quantum mechanics.
So let's start with that first map, the brain's apprentice, neuromorphic computing.
Yeah.
You mentioned the von Neumann bottleneck. I hear that term thrown around a lot. But for the uninitiated, is it just about speed? Or is it structural?
It's fundamentally structural. Think about the device you're using right now, your laptop or your phone.
Okay.
Inside that device, the memory, where all your data lives, and the processor, where the thinking happens, are separated. They're two different neighborhoods.
Right.
Every time your computer wants to do a calculation, it has to fetch data from the memory neighborhood, commute it over to the processor, do the math, and then send the answer all the way back.
So it's a commute. It's like if I had to drive to the library every time I wanted to remember my own phone number.
Exactly.
Yeah.
And that commute is expensive. We call it the memory wall. As processors get faster, they spend more and more time just, twiddling their thumbs, waiting for data to arrive.
It creates a traffic jam.
A huge traffic jam. And physically moving those electrons back and forth costs energy, a lot of it.
And clearly the human brain doesn't do that. My neurons aren't commuting to work every morning.
Precisely. In your brain, memory and processing are co-located. They happen in the same place, right at the synapses. Neuromorphic computing is trying to replicate that architecture.
Okay, so how does it do that?
Instead of rigid logic gates that separate storage and action, it uses something called spiking neural networks, or SNNs.
Spiking neural networks, that sounds aggressive.
Yeah.
How does an SNN differ from the standard AIs we see in things like ChatGPT?
It all comes down to being event-driven.
Event-driven?
Think of a standard video camera recording an empty hallway. It's recording, say, 30 or 60 frames per second, processing huge amounts of data, pixel by pixel, even when nothing is happening.
Right. It's burning energy to tell you that the wall is still white.
It's working hard to do absolutely nothing. It's incredibly inefficient.
Okay.
A neuromorphic sensor, or an SNN, acts more like a biological eye. It just ignores the static background. It only spikes or sends a signal when something changes.
When a person walks into that hallway?
Exactly. If there's no event, there's no energy consumption, the neurons just stay silent.
So it's the difference between a constant stream of heavy data versus just sending a text message saying, hey, something moved.
That's a perfect analogy.
Cool.
And the energy savings are staggering. Look at IBM's True North chip.
Oh, yeah, a pioneer in this field.
It was. It features 1 million neurons, structurally mimicking the brain, but it consumes only 70 milliwatts of power.
70 milliwatts. Hang on, let's get some context for that. What does a standard GPU use?
A high-end GPU running AI models can easily draw 300 to 400 watts.
Watts, not milliwatts.
So we're talking about power density difference of like orders of magnitude. True North is operating on the energy budget of a hearing aid battery.
That is just wild. But True North has been around for a minute. I know Intel has been making moves here too with Loihi.
Yes, Intel is pushing the envelope on the learning side with Loihi 2. See, True North was great at inference running a model you'd already trained. But Loihi 2 facilitates on-chip learning. It has adaptability.
So it's not just executing orders, it's figuring things out on the fly.
Exactly. It creates a system that can learn in real time, without needing to connect back to a massive server farm to, update its brain.
And that brings us to the so what factor. Why does this matter? Is this just so my phone battery lasts longer?
That's part of it, for sure. But the real application is edge AI.
Edge AI.
Think autonomous vehicles, robotics, sensors in remote locations. If you have a drone inspecting a pipeline in the middle of nowhere, it can't afford to upload terabytes of video to the cloud just to check for cracks.
No way. The connection isn't there. The power isn't there.
It needs to process that data right there, instantly, using almost no battery. That is where neuromorphic shines. It brings the intelligence to the data, rather than sending the data to the intelligence.
Okay, so we have the digital brain, super efficient, biologically inspired, great for the edge. Now let's pivot to the heavy hitter, the quantum leap.
The reality simulator.
Right. Now, we've covered quantum a bit before, but the context here is different. We're talking about fault tolerance. But first, maybe a 30-second refresher, why is quantum so different from the silicon in my laptop?
Well, your laptop thinks in binary, ones and zeros, heads or tails. It has to check options one by one.
Right.
A quantum computer uses qubits, which leverage superposition. They can be heads, tails, and a complex probability of both at the same time.
Which lets them explore massive solution spaces. Every possible route on a map, for example, all at once.
Exactly. It's an exponential advantage for certain problems, like optimization. But there's a catch.
These qubits are total divas.
They are incredibly fragile. We call it noise. A tiny change in temperature, stray atoms, electromagnetic waves, anything can knock a qubit out of its delicate state.
And that causes errors.
A lot of errors. And for a long time, the error rate was so high that the computers were practically useless for complex calculations.
And this is where fault tolerance comes in, or FTQC, fault-tolerant quantum computing. This is the holy grail, isn't it?
It is. FTQC is the ability of the system to continue operating correctly even when individual components fail or get confused by noise. It's the difference between a house of cards that collapses if you breathe on it and a brick building that stands up in a storm.
And we have some breaking news on this front. Google's Willow chip, I saw the stats on this, and they're just staggering. 105 superconducting qubits. And it performed a calculation in 5 minutes that would take a standard supercomputer.
What was it?
10 to the power of 25 years.
That is longer than the age of the universe, by a lot. Significantly longer. But frankly, the speed isn't even the most important part of that announcement. We already know quantum is fast.
The breakthrough was the error rates.
That's it. Because usually when you add more qubits, you add more noise. Right. It gets messier.
Yeah.
Like adding more people to a Zoom call, eventually no one can hear anything.
Right.
Historically, yes. But with Willow, they demonstrated exponential error reduction. As they scaled up the logical encoding, grouping physical qubits together to form one reliable logical qubit, the errors actually went down.
That is the game changer. It proves that building a massive, reliable quantum computer is actually, physically possible.
Exactly. It's not just a theory anymore. It validates the roadmap. Yeah. And that roadmap relies on what I call the unholy trinity of quantum robustness.
Okay.
You have error suppression, error mitigation, and error correction.
Let's unpack those because they sound similar, but I know they're distinct strategies.
They are. Think of it like listening to music in a very noisy construction zone. Yeah. Error suppression is proactive. It's like putting on noise-canceling headphones.
Okay, stopping the noise from getting in?
You use control signals to cancel out unwanted energy shifts before they happen.
And mitigation?
Mitigation is more like post-processing. You know errors happened, so you use software to statistically estimate what the real answer should have been. You're basically using an equalizer to boost the vocals after the recording is done.
It cleans up the result, but doesn't fix the source.
Right. And then you have the holy grail, error correction.
The real deal.
That is detecting and fixing errors in real time during the computation without breaking the quantum state. That's what allows you to run algorithms for hours or days, not microseconds.
Which is what Google's Willow is pointing toward.
That's the promise.
So, recap time. We have neuromorphic computing, efficient, adaptable, brain-like. We have fault-tolerant quantum computing, overcoming error problems to become an optimization monster. Here is the million-dollar question. What happens if we smash them together?
This is where we enter the realm of NQC, neuromorphic quantum computing.
NQC. Okay. Is this just using a quantum computer to run a standard AI program?
No, and that's a crucial distinction. We aren't talking about software here. This is physically building neural networks out of quantum hardware.
A quantum neural network, but how? How do you build a synapse, which is a biological memory connection, out of quantum particles?
A synapse needs plasticity, right? It needs to get stronger or weaker.
Exactly, it needs to learn. And to do that in the quantum realm, you use something called a quantum memristor.
A quantum memristor. Okay, that sounds like a prop from Star Trek. Captain, the quantum memristor is overheating. Break that down for us.
A memristor is basically a resistor with memory. In your brain, if you practice the piano, the synapses involved get stronger because electricity flows through them often. They have a history. They remember.
A quantum memristor does the exact same thing, but in a quantum circuit. It changes its state based on the history of signals, in this case photons, that have passed through it.
So it's a quantum component that can remember its past.
Correct. And because it's quantum, it can process information in superposition.
Ah.
So
Yeah.
imagine a brain that can learn from experience and adapt to new data, like a neuromorphic chip, but can also explore a billion different solutions simultaneously, like a quantum computer.
That is the quantum brain.
That is the vision. Instead of programming a quantum computer algorithm by algorithm, which is incredibly difficult, you could potentially just train a quantum brain to solve the problem.
So we stop writing code and we start teaching the machine.
You present it with data,
Mhm.
and it rewires itself using quantum superposition to find the optimal path.
That sounds incredible, but also maybe a little terrifying. Which actually leads us perfectly into the next topic, security. Because when I hear AI, I worry about safety. And when I hear quantum, I worry about them breaking all our passwords. But you found something suggesting that this convergence, specifically the neuromorphic side, might actually make things safer.
It's a fascinating paradox. We often think of these advanced systems as fragile, but in the context of adversarial attacks, spiking neural networks are surprisingly robust.
Adversarial attacks, that's like when someone puts a sticker on a stop sign and the self-driving car thinks it's a toaster, right?
Exactly. You change a few pixels, changes that are invisible to the human eye, just mathematical noise, and a standard AI completely fails. But SNNs handle this much better.
Why? Is it because they are spiking?
It's because of how they encode information, specifically something called time to first spike, or TTFS coding.
Time to first spike. It sounds like a race.
It is a race. In a standard neural network, all the data is processed at once. The noise and the signal are all mixed together in the math.
Okay.
But in an SNN using TTFS, stronger, more important signals cause a spike earlier in time.
Ah, I see. So the important stuff, the actual image of the stop sign arrives first because it's the strongest signal.
Exactly. The stop sign part of the image spikes the neurons immediately.
Right.
The toaster noise, the perturbation, usually affects the background or less intense pixels, so those spikes arrive later.
So the network can basically say, I've heard enough, it's a stop sign, and just ignore the rest.
We call that an early exit. If the network can make a confident decision based on the early clean data, it can simply stop processing before the noisy adversarial data even hits the system.
That is brilliant. It's like tuning out a heckler because you already heard the punchline.
It's a great analogy. And the numbers back it up.
Yeah.
SNNs train with a technique called fused encoding, which mixes different ways of processing input, achieve twice the robustness of standard neural networks on attacked data sets.
Twice the robustness. That is a massive margin when we're talking about safety-critical things.
Absolutely. If you're sitting in a self-driving car, you want that car to ignore the sticker on the stop sign. This temporal aspect, the timing of data, is a hidden superpower.
It turns time into a filter for truth.
In a way, yes.
So we have efficiency, we have power, and we have security. But I have to ask the practical question. When is this actually happening? Is this science fiction, or is it coming next Tuesday?
It's a mix. We really have to separate the timelines.
Okay, let's look at the roadmap. Neuromorphic first.
Neuromorphic is here in the early stages. You can buy chips like this for research right now. We expect them to become widespread as co-processors in edge devices, phones, cars, smart cameras, within the next 3 to 5 years, so maybe 2028 to 2030.
That's pretty soon. We'll probably have a neuromorphic chip in our pocket without even realizing it.
Very likely.
What about the fault-tolerant quantum side?
That is a longer haul. Despite the Google Willow breakthrough, we are likely 10+ years away from large-scale commercial quantum computers that can solve problems we actually care about, like in finance or chemistry.
So we're in the early fault-tolerant era.
We are. We have the physics proving it's possible, but the engineering is massive.
And the merger. The neuromorphic quantum computer.
That is very much in the lab phase. We have proofs of concept, like the single quantum memristor we discussed. But scaling that up to a full network, that's deep future tech.
But knowing how fast tech moves, deep future might be closer than we think.
Well, Here's a provocative thought to leave you with. We are obsessed with waiting for perfect quantum computers, ones with zero errors.
Right.
But biology isn't perfect. Brains are noisy. They are messy.
That's true. I forget where I put my keys all the time. My neural network definitely has error rates.
Exactly. But you still function. You still drive a car, solve problems.
Mm-hmm.
So perhaps the shortcut isn't to wait for perfect quantum machines. Perhaps dirty or noisy quantum neural networks, which embrace the noise just like our brains do, might actually be useful sooner than the perfect ones.
So we might be building a messy, noisy quantum brain before we build a perfect calculator.
It's very possible the noise might not be a bug. In a neural network, it might actually be a feature that helps it generalize.
That is a lot to process. So let's recap this journey. We started with the digital brain of neuromorphic computing, ultra-efficient, event-driven, breaking the von Neumann bottleneck.
Then we looked at the reality simulator of quantum. We saw how Google's Willow chip is proving that we can beat the error problem with fault tolerance.
Moving from theory to engineering.
Exactly.
And then we merged them into the sci-fi reality of neuromorphic quantum computing, using things like quantum memristors to create hardware that learns.
And finally, we discovered that the temporal nature of these systems, the timing of the spikes, offers a massive advantage in security against adversarial attacks.
It really changes how you look at the future of AI. It's not just about bigger software models, it's about fundamentally rethinking the hardware itself.
Absolutely. We're moving from a world of static computation to a world of dynamic, adaptive, and perhaps quantum mechanical intelligence.
If you want to dig deeper into one specific area we touched on today, I'd encourage you to look into spiking neural networks, and specifically that concept of time to first spike. If you're interested in AI security, the idea that time is a defense mechanism is the next frontier.
It's definitely a space to watch.
Thank you for listening, and see you next time on AI Affairs.